Well, it may be a good time to talk a little bit about the projects. For the curious students, you should have encountered this list. If you scroll down on your on the Facebook page of this course, you will see this post. It gives just some example project topics. These topics are still valid, so you may choose one of them. These projects are suitable for groups of 4 or 5. Okay, so you may choose one, or you may think of one. As a matter of fact, the last topic over there is, as you see, any other real-life problem involving signal processing methods or the design of a system. That's also fine. That's also okay. But since next week it will be a holiday, we are running out of time. So the week after the holiday, the first week on Monday, you should already prepare your project proposal. Okay, you have to prepare your project proposal with your names on it, emails as well. And the project proposal must be prepared in a legitimate manner with all the necessary information, like who is doing what is the time schedule for your project, what are your intermediate deliverables, what will you do in the intermediate steps, and in the end, what will you get? What do you propose to get? The deadline is the final week, where you have to submit a project report. Not a very big one, not a big deal. Okay, whenever I'm talking about papers and documents, I don't mean a lot of pages, but I mean legitimate and meaningful things. So the project report should also be quite brief, but it must have all the necessary information in it. And together with the project report, which is in the same format as the 4th year graduation project. Have you ever seen a 4th year graduation project, or are you doing one, or do you know what they look like? You should take a look at them. They have a format. There's an abstract, there's an introduction where you give the history and all the available information. And after that, you focus to your method. And you describe your method. Then you describe your experiments, experimental results, set up, how you set up the experiments, and what are your results. And you conclude by what you get from that project. And you have references, which you shouldn't forget. So that's a methodology, and you should obey that method as well in the final week. And you have to, of course, present it as well. Every group will present their work in 10 or 15 minutes, okay, just to show what the topic was and what it means, and just run something if you have something running, or if you have something hardware, just show its work, and then that's it. That will be the presentation. You should also prepare a presentation then. By the way, if you try to take a look at the past posts of this lecture, you will, for example, you will, for example, see this one as well, which is a PDF of a crib sheet, and I ask students to print it and bring with you during the exams, in the first exam, in the second exam, and in the final. If I have any extra information, I'm also gonna put it so that you will know. So follow the Facebook page. How am I gonna go back? There are some book informations, all those things. So pay a little bit attention to this. Now, okay, we can continue. By the way, the emails at the cover page of your proposal is critical, because if there's a problem about your project proposal, if it's not legitimate enough, or if it is if it has flaws, then I can get back to you with the emails. Okay, just so indicate your emails over there as well. If I don't return back to you within a week, that would mean that your project is okay. You can continue with it. All right. In any case, your project is okay. I may just ask something extra. This is missing, so you should put that as well. So you must perhaps start about your project today. Choose a topic or invent a topic. Assume that it is selected already. Just start thinking about it. You don't have much time. You're running out of time. Next week is a holiday, but on holidays everybody is busy, so you will not have time to work on it. Be careful and be warned, at least. Now, the first thing that I want to mention is the convolution properties. Convolution operation was like this, if you remember. Let's say y of n is equal to x of n convolution h of n, and that corresponds to an LTI system. And previously I was writing s inside the system to indicate a system, but now I'm putting an h of n, which is already providing you with the information that it is an LTI system and it has an impulse response h of n, which must be given to you. And this is the input-output relation from x of n to y of n. Strangely, convolution it's a linear operator, therefore it has this kind of a property too. Y of n is also equal to h of n convolution x of n as well. So it doesn't matter which one you flip around, or these two equations are identical. What was our first convolution summation? It was m from minus infinity to infinity x of m h of n minus m, right? This is what I have written. And I'm now saying that this is also equivalent to summation, it's a bad summation, sorry, m from minus infinity to infinity h of m x of n minus m as well. It's the same. So the response is not aware whether it was the input or it was the impulse response that produces the output. In other words, the system is equivalent to this. H of n is an input signal. H of n is an impulse response, but it's a signal. You can just, it's a function. You can draw it on the discrete axis. Just think of it as a signal input to a system whose impulse response is x of n. And the output is again y of n. Okay. What other properties do we have? We have this, for example. If you have two signals added as an input to a system, then you should convolve this summation with h of n to produce y of n. Okay? This is equivalent to, as I have indicated in the last hour, individual convolutions with the separate components of these two signals. Like this is equal to x1 of n convolution with h of n plus x2 of n convolution with h of n, and this is also equal to y of n. And that's why I'm telling you that you can split your signal, your x signal, into components, simpler components, and then perform the convolution with h. You must have separate convolution results, and then you must combine those convolution results. This is possible. So in that essence, it's like multiplication with a scale, right? This is a summation and it's distributed. It's like the previous was the commutative property. You can interchange. The h and x can commute. This is the distributive property where convolution is distributed on summation. Well, let me write them even in a more general form. I like such things, as you see. Summation xi of n. We have a lot of signals, summation of signals. Convolution with h of n is equal to summation I in parentheses xi of n convolution with h of n. These two are the same. You may first convolve and then sum, or you may first sum and then convolve. Now from the commutative property we come up with something strange here. This also means that if you have an input x of n, and if you want to convolve it with a summation of impulse responses h1 plus h2 of n, then this also distributes similarly, because these two can be interchanged. You can split, in other words, the impulse response into components as well. You can split both of them. And this will be equal to x of n convolution with h1 of n plus x of n convolution with h2 of n. Now this kind of a summation in h1 and h2 can be graphically illustrated as a system layout too. What kind of a system does it correspond to? What corresponds to, suppose that you have two systems. One of them is with the impulse response h1, the other one is with the impulse response h2. How do you combine them in such a way that this operation is needed? In other words, the effective impulse response corresponds to the summation of these impulse response term by term. What kind of a system is that? It's a parallel system. You can see it from here too. In one branch, the input signal passes through the first system, h1, and it produces an output. In another branch, it is convolved with h2 and produces an output, and those two outputs are added eventually. This is the formula for that. And therefore, this situation corresponds to this. This is x of n, and this is y of n. If therefore you have such a parallel system, then the effective impulse responses are term-wise added. Clearly, if this is one possibility, then there is another possibility that systems can be cascaded in a series manner. No, it's not x1, sorry. It's x of n going into system with impulse response h1 of n, and the output goes into another system h2 of n, and this is the output y of n. Then what? What is the effective system? Suppose that we have a larger system here with input x and output y. What is the impulse response of this H equivalent system? Series, yes. What is H equivalent of n in terms of H1 and H2? H1 times H2 is one proposal. Any other guesses? It's not summation. Summation was the previous. Now, remember this. Whenever you pass a system a linear time invariant, an LTI system, the operation is not multiplication, it's convolution. You convolve x of n with h1 of n, and that convolution is there. It is a temporary output, let's call it y1. And then that must also be further convolved again with h2 of n. So y of n is this. It is convolution of x of n and h1 of n. And this result must be also further convolved with h2 of n. Now the situation here is, from the linearity of convolution, the place of the parentheses is unimportant. It doesn't matter which you convolve first. You can interchange their places. You can perform a convolution with this one and that one first. In other words, you can first convolve x of n with h2 of n, and then the result can be convolved with h1 of n. That's also possible. But better yet, you can convolve h1 of n with h2 of n first, and then you get something. With that something you convolve x, and that something is this h equivalent of n. So the equivalent system response is the convolution of these two impulse responses. It's not the multiplication, it's not the summation, it's the convolution of the two. If you have 3, then what? It's the convolution of the 3. Which convolution will you perform first? It's up to you. Just convolve the first one with the second one, and then the result will be convolved with the third one. That's okay. Or the third one with the second one first, and then with the first one. It doesn't really matter, but you have to convolve. Multiplication is a very dangerous trap in system representations. And many students, when solving problems, they immediately fall into the trap of just first multiplying with something, but the result would be completely different, of course. Convolution is the operator to produce the output. Okay, so the equivalent system is h1 convolution with h2. An example, h1, h2. I'm not putting n's here. h3. What is the equivalent system response? Then the equivalent system response is equal to, of course, h1 plus h2 convolution h3. You can then distribute. You can say h1 convolution h3 plus h2 convolution h3 as well. So the system's impulse responses are convolved in time domain. Fine. In the last stage, I quit putting the square bracket n terms because these properties also hold in continuous time too. In continuous time, we do have convolution, but first, so the title is continuous time convolution. Continuous time is abbreviated as CT, discrete time is abbreviated as DT. First I will write again the discrete time convolution. Y of n is equal to summation m from minus infinity to infinity, x of m, h of n minus m, where h is the impulse response. Do you remember the continuous time impulse? Delta t, continuous time impulse. It was a very bad signal. Its magnitude was, its amplitude was infinity, its width was 0, but the area under it was 1. So 0 times infinity for that particular case, it was 1. So it's not the signal itself that you can use. You can only use the area under it. But suppose that somehow magically, by the way, it's not possible. I'm sorry to say that. But suppose that somehow you could get an impulse, which is not a physical signal in time domain reality, but suppose that you have it. What you can do is you can make a black box experiment, apply it to the system, continuous time system, and observe the output. What will be the name of the output? The name of the output will be impulse response, right? So we do have the same thing in continuous time. We have the impulse response. Unfortunately, it's very mathematical, and it's very difficult to physically achieve an impulse response. Because we have the signal generators in the lab, right? It's not possible to generate an impulse. So you cannot literally measure the impulse response. But this is mathematics that we are talking now. And it will help us solve real life problems too. You cannot, for example, obtain an impulse, but you can literally obtain a unit step, for example, and unit step and unit impulse are related, so there are ways to do it. But forget about it for the time. Say that we have an impulse response. Which acts like this. Y of t goes into an LTI. It's a continuous time LTI system. And the output, delta of t going into the continuous time LTI system, and you observe y of t, and we will call this y of t as the impulse response, and we will use the same notation. It's not h of n, of course, this time it's h of t, which is the impulse response. Let's assume this kind of an input-output relation. Then, this convolution operator will have an analogous, a simple form in continuous time too, like this. Y of t, just try to convert everything discrete time at the top to continuous time at the bottom. Y of t is equal to, will it be a summation? No, summation is in discrete time. We will use an integration from minus infinity to infinity. Now, the integration running time is like the running time here, which is m. And m is different from n. N is time, n is the parameter that we use. So we have to use a different parameter for the running time instead of t. T is the time. So it will not be dt, an integral, something dt. It's not like that. If you write it like that, there will be no t left to the output. The output will have nothing to do with t. The output must be parametric in terms of t, therefore you cannot use dt. You must use something else. And the book uses the Greek letter tau. Do you know that? Just something like this. So m goes to tau. That kind of a letter. Okay? Instead of, n goes to t and m goes to tau, in other words. And we have x of tau, x of m translates into x of tau. H of n minus m is t minus tau. We have to put a d tau here. So this is it. That's about it. This is the convolution formula in continuous time. In the book, if you follow this chapter, you will see that they try to first make your signal in terms of very small impulses. But in the very small impulse explanation I find quite complicated. So I don't want to waste time in trying to first indicate x of t in terms of impulses. But that may also be quite reasonable for you. the book attempts to find the formula like this. It first says that x of t in terms of impulses, well, we will start from the discrete time. X of n in terms of the impulses was what? It was the convolution sum. It was m from minus infinity to infinity, x of m delta n minus m, right? This was the convolution sum, which is translated into continuous time like this. X of t is equal to integral from minus infinity to infinity, x of tau delta t minus tau d tau. So this is the way to represent our signal x of t in time domain. You see, in time domain, the representation also requires the knowledge of the magnitudes at every time instant. X of tau at a certain tau value corresponds to the value of that signal. For example, when tau is equal to 0, x of tau at tau is equal to 0 is the same as x of t at t is equal to 0. These are therefore the magnitudes or the values, and these are the shifted impulses. So this is also a combination of shifted and scaled by this value impulses. It's a combination of impulses. Those impulses were arrows, you remember that? You have a lot of such arrows everywhere, but indefinitely close to each other, and then you integrate. You combine all those integrals somehow, the impulses somehow. So this is your convolution integral. Then x of t is equal to integral x of tau delta t minus tau. When this goes into a system whose impulse response is h of t, always keep in mind this. What was the impulse response? It's the name. It's the response of the system to an impulse. When an impulse comes in, impulse response goes out. So tell me this. What goes out if delta t minus tau goes into the system? If delta t minus tau goes into the system, what is the response? ht minus tau. The impulse response will be shifted by tau. So every delta t minus tau will be, the output will be h of t minus tau at the output. What is the response to this impulse? X of tau delta t minus tau. X of tau is a value, let's say it's 3, 5. What is the response to 5 times delta t minus tau? The response is 5 times h of t minus tau. So what's the response to x tau times delta t minus tau? It is x tau times ht minus tau. If you combine with the integral at the top, due to linearity, you can also combine at the outputs. So each separate things will be translated like this, and the accumulation will also be accumulated at the output level. And the result will be y of t from minus infinity to infinity, of course. So this is the convolution you can think of. But since impulse is not very physical, like in the discrete case, I cannot think of separate or individual impulses and separate or individual impulse responses. These impulses are very close to each other, so it's a little bit complicated. You may prefer to just memorize this convolution. Fortunately, this convolution, the graphical method of performing this convolution is identical to the graphical convolution in discrete time. And we can begin with some examples. Suppose x of t is equal to e to the minus at u of t, which is a decaying exponential for a positive a. So this input is, it's all zeros, and then from 0 it jumps to 1 and then decays with a complex, with an exponential factor of a, okay, e to the minus at. That kind of a shape. So it was all zeros and then jumps to 1 and then decays. Something like that. Well, it's a bad illustration. Alright. So this is x of t, let's assume. And let's have the impulse response h of t. These two must be given to you. You must have the input and you must have the impulse response. Only u of t. Do you remember a similar question from yesterday? Yesterday we solved the same question in discrete time. It was a decaying exponential in discrete time, and the impulse response was the unit step, or vice versa. You can change. You can always say that the input was u of t and the impulse response was e to the minus at u of t. It doesn't really matter, but it's the same question. So this is the impulse response for our question. And the question is, of course, what is y of t? You just need to convolve. If you have some mathematical expressions like this one, you can think of the graphical way of trying to obtain a formulation. Yeah, let's first start with the mathematical, the graphical way of solving it. So let's flip around h of t. When we flip it around, we get this, right? The red curve to the left. Then we just have to slide it by an amount of t. The amount of this slide will correspond to the output. And we need to overlap that with the input. At this particular point of shift, there is marginally no overlap. Okay? The overlapping is 0. If I go to the right, there will be overlap. If I go to the left, there will be no overlap. So for the positive times, I will have some overlaps. Let's go to the right by an amount of t prime. Okay, let's go to the right. Then what will be the overlap? The overlap will be here in this range at the same t prime. What's the multiplication of these two functions in this overlapping region? So I'm trying to find the y of t at t is equal to t prime, or y of t prime in other words. It's the area, the integral area between these two, it's the area under the multiplication of these two overlapping regions. What is the multiplication over there? The multiplication is the same as this. It's e to the minus a t. The multiplication function is that. But the starting, because the magnitude of the below figure was 1, it was unit step. If it is something else, then you must multiply, of course. Time-wise, multiply the values. The multiplication of two functions may be something different. But this magnitude is 1, and the 1 multiplying e to the minus at will give you e to the minus at. From where to where? From 0 to t prime. Right? dt. Or it may be a better idea to put tau, e to the minus a tau d tau sort of thing. That would be more reasonable. But nevertheless, this is it. This is the integral that you must evaluate to find the convolution result. And what is that integration? It's equal to, there's a minus 1 over a from the integral, and e to the minus at from 0 to t prime sort of thing. and that would be equal to, let me write the exact solution, 1 over a in parentheses 1 minus e to the minus a t prime. Okay. This is the integral, and I can immediately say that the convolution result is therefore y of t is equal to, I will first open a curly bracket, it's equal to 1 over a 1 minus e to the minus a t for some certain values of this time. This is valid as long as that t is greater than 0. T greater than 0. And it's equal to 0 when t is less than 0. Because there is no overlap. You shouldn't integrate. You shouldn't perform the integral. What is a better way of writing the same thing? You remember from the previous lecture. 1 over a 1 minus e to the minus a t u of t. Okay, just stamp that u of t over there because everything starts from there. Yeah. Yes, that's a very good question, and I was about to mention that. What's happening at t is equal to 0? I mean, one of them is for t greater than 0, the other one is for t less than 0, where this is a continuous shape. So at t is equal to 0, it is 0 both at the top and at the bottom. So whichever equality condition you put, for example, here, that would be the same for this one. So in the if the impulse response or the signal itself doesn't include impulses, critical, this is critical, then the convolution result will be continuous. Do you remember the convolution result of two rectangular box shapes? What was the convolution of two rectangular box shapes? Yeah, a triangle. Now if you convolve two rectangular boxes in continuous time, it will again be a triangular shape. A triangular shape, by the way, is continuous. But a box shape is not continuous. If you convolve two signals, and as long as they don't have any impulses in those signals, as long as they are just shapes, no matter how sharp those shapes can be, when you convolve them, the convolution result will be continuous. Okay, that's why that equal to 0 situation is not quite critical here. So this is the convolution result, and we didn't do it quite similar to the discrete time case, because now we have integrals, so you have to be careful about how these two signals overlap. It may be a good idea now to start mentioning that rectangular example. So from, do we have such an example? Well, whatever. From minus 1 over 2 to plus 1 over 2 in time, this is 1, and that is x of t. The magnitude is 1. And again, the same shape. Well, let's not make it the same shape, let's scale it a little bit. Well, let's say this is 2, and this is 1 over 3. 1 over 3 for h of t, the impulse response, again from minus 1 over 2 to 1 over 2. What is the response of the system if the input is x of t and the impulse response is h of t? Or in other words, what's the convolution result? This convolution result must be provided or given in piecewise linear, in pieces, in other words. The previous one was a single entity, a single formula at the top, you see. But this one, well, I am sure you won't be able to say it that way. You just have to think of flipping around. H of t will give you the same, right? This, because it's symmetric around the center. So when you flip it around, it will be the same. Let's slide it towards left. And let's slide it up to here, to the left. How much sliding does it correspond to, by the way? It corresponds to a slide of -1. That's to the left. Now that red box at the left is not overlapping with the top x of t. Okay, so there is no overlap at -1. This is -1/2. This is -1. This is 0. There is no nothing at -1. If you start sliding towards right a little bit, let's come here. Okay, the dashed box, the dashed red box. How much overlap is there? It depends on how much shift to the left it was. To the left, it's an amount of, let's call it t prime. This point is the center of the dashed box is t prime, so it's a shift to the left by t prime. If that t prime is greater than -1, to the right of -1, then there is some overlap. And what is that overlap? How much is that overlap? Or what is the area between this point from -1/2 to here, which is the ending point of this box, and that box, let's draw it here. It was something like this. The multiplication of the two in the level will be equal to 1/3 times 2. So the multiplication will be a box shape. Where am I going? Yeah, let me draw it here. It will be a box shape with magnitude 2/3 somewhere here. The level is 2/3. It starts from -1/2 and it goes up to somewhere. What is that somewhere? Say it. T plus 1 over it is equal to well, t prime plus 1/2, because t prime is already negative. Yeah, okay. So this point is t prime plus 1/2. Yeah. So these two are the limits that you have to evaluate. The integral, and the integration is to find the area underneath. So the distance between -1/2 and t prime plus 1/2 is t prime minus 1. -1/2 minus t prime plus 1/2 is minus t prime minus 1. And minus t prime is where is it? Minus t prime. T prime is here. It must be somehow minus t prime plus 1. Okay, I'm sorry about that, but the difference between the two must be somehow t prime plus 1, or 1 minus t prime, which is the width of this rectangle. And the height of the rectangle is 2/3, so the area underneath is 2/3 times 1 minus t prime must be the area. That area, as you see, is increasing. T prime was originally, or is it a plus? I'm being confused here. T prime is already negative, so it must be a plus. t prime is already negative, and it's a value like minus 0.7. So 1 minus 0.7 is 0.3 sort of thing. Okay, this is my final result. So this thing is increasing as t prime increases from minus 1 to, let's say, 0. Okay. Then the overlap between this left-hand side red box will be maximized. It will be completely overlapping in the center. And if you try to draw it, it would be something like this. An increase, a steady increase up to 0. And at 0, it reaches to a point. That point is the legend that you must mark in your graphic. And that legend is what? It's the multiplication of these two rectangular boxes. The multiplication will have a level of 2 times 1 over 3, that is 2 over 3. And the width is 1. 1 times 2 over 3 is 2 over 3. It will reach to 2 over 3, the triangle. And afterwards, it will start linearly decreasing back to 0, where it will go back to 0 at plus 1, because when it comes here this time, the overlapping will be nothing. So it's a steady decrease to 0, and this will be equal to, y of t over the axis of t. Okay, so this thing shows you about the methodology to perform convolution. This is one of the simplest examples, and even in this example, the time shifts, negatives, the area being occupied, all those things are a little bit confusing already. When you have shapes, this confusion is almost mandatory. Before your question, let me write the next question, and then I will listen to you. In the next question, let's start thinking about the convolution of this box up to t from with a value 1 starting from 0. This is x of t, and the impulse response is given as this up to 2t. It's a steady increase and then abruptly coming back to 0. So when we convolve them, when we convolve these two, what's going to happen? It's a headache. This time you flip around this h of t and then start overlapping, and those overlappings will make some triangular shapes. So you have to evaluate the area of a triangle, not a rectangular shape, but it will be a triangular shape. It will have, where will be the maximum? You may start thinking about that. Huh? Where is the maximum? I guess it should be 2t. When you flip around this, it will be like this. And then when you go by t towards right, it will be this triangle overlapping with this rectangle, and it is only overlapping with the smaller portion of the triangle. So if this triangle is pushed further to the right and goes like this, the amount of overlap multiplication will be maximized. So the maximum of these two shapes will be achieved at t is equal to 2 capital T. But can you write the formula from 0 to t, t to 2t, 2t to 3t, and 3 to onwards? It must be, you must give piecewise formulations of these things. For this one, you must give the formula for this inclination from -1 to 0. You must give the formula for this line from 0 to 1. And you must also give the formula for the rest before -1 and after +1. Piecewise formulation. Now,
Hocam bir önceki soruda iki tane eksi 1/2'den başlayan sinyalimiz birleştirdiğimizde nasıl eksi 1 ile eksi 1/2 arasında bir elde edildi? Orada bir üst üste geçme falan yoktu kareler arasında.
No. This t prime is here, you see. It's a rectangle, it's the center of the rectangle is greater than -1/2. To the right of, it's greater than -1, it's to the right of -1. Therefore, you are here. And if you draw a box centered around this t prime, there will this portion will be definitely to the right of this -1/2, which is here. So we have some overlapping region here. And that overlapping region is the one you have to evaluate to find the area underneath. And when you push this t prime further to the right, the amount of overlap will be even larger. And when t prime becomes 0 in the center, they will completely overlap with each other. And when they completely overlap with each other, when t prime is equal to 0, the area is 2 times 1/3 will be the level, and it will be from -1/2 to +1/2. So the width is 1. 1 times 2/3 is 2/3. That's the area. So that's why it's increasing up to 2/3.
Hocam neden sinyalin orta noktasını aldık? Oraya
It is given that way. I gave you x of t like this, and I gave you h of t like this. So I'm shifting with respect to the center point. When I flip around h of t, which was originally this shape, let me draw it again. This was h of t. What is h of minus tau, in other words? If you flip it around, it will be the same. Do you agree with this? So when you shift by something, let's say t prime, when you shift by t prime, that t prime will shift from 0 to t prime in the center. And the boundaries will also be shifted by the same t prime altogether. That's why I'm looking at the center. That is the origin point I'm thinking of. Okay. Now, here, for example, it's not the origin or it's not the midpoint of these boxes or triangles that we have to consider. I'm again taking a look at the origin. For example, if I flip around this h of t, it will be like this, right? H of minus tau on the axis of tau, and this is minus 2t, and this is 0. It's not minus 2, it's minus tau, okay? So you have to go rightwards, push it rightwards, so that these two shapes, x and h of t minus tau, will overlap. For example, when it comes to here, let's shift a little bit. Let's say that it's t prime here. When it is t prime here, how much overlap does it make? The overlap will be here, like that. Do you agree? And the magnitude of this one is 1. Therefore, you have to take a look at the formula of this line. You have to give me the formula for that. Can you? What is the line of this line formula for this? Yes, it's a line. What is it? It's t prime minus t or something like that on the t-axis. Yeah, minus t is the function, and I'm adding t prime to that, so it is pushed upwards by an amount of t prime. So this is the line formula here, and that line formula only intersects with the with this rectangular region from 0 to t between 0 to t prime. And and the area under that integral is this, which is the area under this triangle, and that triangle area is t prime square, isn't it? Over 2. This is the area of the triangle. Now, this as long as I put the t prime here, we are still something easy. What would happen if I go like this and say that I'm evaluating at t double prime, where t double prime is somewhere here? Then what is the shape that I have to evaluate? What is the shape that I need to find the area under? The shape I need to find the area under is from 0 to t, because after capital T, although t double prime is larger than capital T, it is multiplied by 0, so that portion is chopped. There is no intersection there. The intersection is only between 0 and capital T, and I need to find the area under this kind of a shape. Strange. Right? What's the area underneath? I will give you the result, and I urge you, this example is in the book by Oppenheim too, so please follow it, but before following it, try to make sure that you come up with the same equations. The result is like this: y of t is equal to a large square curly parentheses, of course 0 for t less than, for t less than 0, and it's equal to 1 over 2 t square if t is greater than 0, greater than or equal to, doesn't matter, but less than capital T. Because if I go beyond capital T, as you see, it will become a different shape. It won't be a triangle anymore. And the formula for that strange shape is this: capital TT minus 1 over 2 capital T square if T is between capital T and 2 capital T. Yeah. When it is even more, we have a situation like this. For example, like this. Let's say T triple prime. This T triple prime, when it is intersected with this function, will be like this, something like this, and the integration, the intersection will be this shape that I'm drawing now, like this, and you have to find the area underneath this. Strange. And the formula for that is minus 1 over 2 t square plus capital T t plus 3 over 2 capital T square. If t if t is greater than or equal to 2t but less than 3t, because if t is greater than 3t, then it will be something like this, further to the right, and there will be no overlap. So I say it's equal to 0 again when t is greater than or equal to 3 capital T. 5 pieces of the graph. And when you follow what's going on in the boundaries, for example, when t is equal to 0, this is equal to 0, so it's continuous. Before it was 0, and at t is equal to 0, it's still continuous. At t is equal to capital T, this is 1 over 2 capital T square. At t is equal to capital T, this thing also gives you 1 over 2 t capital T square. So they match at the boundaries. At 2 capital T, this will have a value, and at 2 capital T, this value here will be the same. And it goes down to 0, this value goes down to the 0 when t is equal to 3 capital T, which is the same as the last thing. The Java applet is also capable of doing continuous time convolutions. Perhaps in the future week, I will also install that and we will see some examples. But before that, please also do that. Okay? Go to the web page and do some continuous time convolution too and see what's going on.